Hi, and welcome to 11.7, Part 5 and 6. So, Part 5 is all about equivalent resistance, a nice little review of the concepts. It says, what happens to the equivalent resistance as you add more resistors in series? So, hopefully, you remember the relationship from the reference table. And let's draw a little circuit here so we could visualize what's going on. In series, there's only one path. So, let's say we have like that. Boom. And let's say we wanted to add another resistor. How will that affect the overall? Really, you could think of it, how does that affect the current through the whole circuit, the total current, if you add another resistor in series? Because if we can see what happens to the current, then we know overall the resistance did this, the equivalent resistance did this. If the current decreases, that means the equivalent resistance must have increased. And if we add a resistor and the current increases, well, that means there's less resistance, right? The equivalent resistance decreases. And what happens is when you put a resistor in series, there's only one path still for these electrons to flow. So it would do it exactly what you probably think initially. The more resistors you put in series, the less current there's going to be. You're adding more resistance to the circuit. The equivalent resistance increases because there's only one path for the electrons to flow, and the total current decreases. Now, this is a pretty straightforward concept that, the more resistors you add, the more resistance there is. The resistance increases. But 19 is really the tricky one. So what happens to the equivalent resistance as you add more resistors in parallel? Explain why in your own words. So again, we'll start by drawing a parallel circuit. And what does this look like if we add more resistors in parallel? Well, here's our circuit. And if I wanted to add another resistor here, I literally have to change the wiring. I'm making another path by adding this resistor in parallel. And now there's another path for current to flow through. So current can come this way. And now more current is flowing through this branch too, because we have the same potential difference, right? The voltage stays the same from this point to this point and this point to this point. So since the voltage is the same, it's going to push the same current through each branch, provided the same resistor. So since there's like double current here, and then again, the total current is here, and then it splits between this and this. The total current, this is going to increase because there's more current. 1, 2. If you add another resistor, that you're opening up another path with a voltage from here to here, same voltage because it's in parallel. And now there's even more current flowing. There's more room for the electrons to flow. So before, where the series circuit was kind of like a one-lane highway, and if there's more resistors, that's more traffic on the highway because it's only one lane. Everybody has to go at the same speed. So the more resistance in a series, the less current. Well, in parallel, you're totally adding the resistors in a different way. You're actually changing the wiring, and you're giving more paths. You could think of the car analogy, more lanes in the highway. There's more space. Look, if we had like a 17-lane highway, you think there would be ever a traffic jam on that highway? Look at all these paths for the cars to go through. There's not a lot of resistance here overall, and the total current increases. All right, so the total current increases. Therefore, if you were going to make an equivalent resistance, replace all of those resistors with just one resistor with the same total current that we were just talking about there. All right, what would this resistor have to be in order to have this huge current now? Well, if there's a big current, that means that there's less resistance. And overall, you could actually replace all of these resistors with one tiny resistor, and you would end up with the same current. So the equivalent resistance decreases because there's more paths for current to flow and the total current increases. So let's write that down. Oops. The equivalent resistance decreases because you have multiple paths for current to flow and the total current increases. And to support this idea of the relationship between the current and the resistance, you could look at the Ohm's law, R is equal to V over I, and you can see it's an inverse relationship. So for number 19, the parallel circuit, we said that if there's more paths for the current to flow, then overall the total current is going to increase, which makes the equivalent resistance decrease because it's an inverse relationship there. So that's just a little added support with a equation. So number 20, multiple choice. Which segment has an equivalent resistance of 6 ohms? So you could take a look. A, just normal series, 3 plus 2 is 5. B, there it is, 2, 4, 6. All right, so R1 plus R2 plus R3 in a series circuit, that's going to be 6. And then you'd have to do some fancy fraction stuff for C and D. 21, resistors R1 and R2 have an equivalent resistance of 6 ohms when connected in the circuit shown in the diagram to the right. The resistance of R1 could be, okay, so now you have to think about the resistors being added in parallel. Now you might be tempted to take a look at the equation first and do some algebra, but the fact is we don't know these two. They're different. If it said that they're the same resistor, then it would be only one variable and we could probably solve using an equation. But since they're two different variables and we only have one equation and there's no other information given, we don't know the voltage or the current, it seems like we're stuck. So you have to look at your answer choices closely. This is a multiple choice question on purpose. You couldn't do this otherwise unless they gave you a set of answers. So if they're telling you the equivalent resistance, REQ, is equal to 6 ohms, I think we had talked about it in the previous video. Where was it? Way back. Let's see if I could even find it. What a waste of time, Mr. Nangle. What's the concept here? We need to know, okay, so we could use this. For number 9B, the equivalent resistance was 12. Well, this resistor is 18, and this resistor is 36. You're telling me that the equivalent resistance is less than the smallest resistor? Yeah, we have said that before too. It pops up in every parallel circuit. The equivalent resistance is always going to be less. So 6 is less than 15, and we calculated the first one is 10. So the equivalent resistance 6 is less than the smallest resistor. So that's the kind of the concept that we have to remember when looking at this very tricky, but then as soon as you know the concept is actually kind of easy problem. So we know the equivalent resistance is 6. This and this has to be greater than 6. The equivalent resistance is always less than the smallest resistor. So R1 could not be 1 ohm. Nope. Because we're looking for something that's greater than the equivalent resistance, right? It can't be 5, it can't be 4. This could be 8 ohms because the equivalent resistance is less than that. So the correct answer is 8, just from the fact that you don't have to solve for it all. You can't solve for it. There's not enough information. It's a concept problem. You had to remember that the equivalent resistance is always less than the smallest resistor. Tricky stuff. Number 22. What is the total resistance of the circuit segment shown in the diagram below? Hint, if you understand how equivalent resistance works in parallel circuits, you don't have to do any calculations to pick an answer. What the physics are you even talking about over here? Let's see. Oh, well, that's a little disappointing because I wanted to do the fun fraction thing. We can. I'll prove it to you. So it's the same exact concept as number 21, where they're saying, oh, if you know how parallel circuits work, you know that the equivalent resistance is always less than the smallest resistor. Well, the smallest resistance we have is 3. All right? So we're looking for an answer that's less than 3. That's choice A. A is the only one less than 3. Let me prove it to you, okay? 1 over REQ is equal to 1 over 3 plus 1 over 3 plus 1 over 3. What's 1/3 plus 1/3 plus 1/3? 3/3. 3/3 is equal to 1. 1 over REQ is equal to 1. Take the inverse. REQ is equal to 1 ohm. Boom. That's the answer. Tricky stuff. 23. In which circuit would ammeter A show the greatest current? So if we're looking for the greatest current, I is equal to V over R. I'm thinking that since we're talking about equivalent resistance, we want this to be big. We're going to want a small resistance. So really, yeah, because the voltage is the same everywhere. So really, they're just changing the resistance. And if we're looking for the greatest current, we want the smallest resistance. That's what we're looking for over here. So definitely not going to be a series circuit because you just add up the resistances. For the equivalent resistance for A is 10 ohms. Nope. B is 5 ohms. And by looking at C and D, I can tell it's going to be greater than or less than 5 ohms there. So which one has the smallest equivalent resistance here? Well, we said the more resistors you add, the more path for electrons to flow, and that will increase your current. And you could, if you wanted to be diligent, you could calculate the equivalent resistance of these things. Let's see. It would be 3 over 5, 5 over 3. So whatever 5 over 3 is, that's the equivalent resistance for D. And then 2 over 5, 5 over 2. So 2.5 ohms is the equivalent resistance for C. It's going to be choice D. I could tell without even doing any calculations. Moving on. Part 6, beautiful. Drawing diagrams. It's important to be able to draw and analyze your own circuit diagrams. By convention, straight lines are used for wires normally bending at 90-degree angles. Draw a diagram for the following circuits using the symbols in your reference table. A series circuit consisting of a 12-volt battery. Okay, 12-volt battery. And let's like label them so we know. A 10 ohm lamp. So here I go, making my wires. 90-degree turn. There's my lamp, a little pigtail with the circle. And a resistor. So we know that this is 10 ohms, but we don't really know the resistor yet. Let's see. Anything else? There's an ammeter measuring the current of the circuit. Okay, so we have to add in an ammeter over here. And there's a voltmeter measuring the potential difference across the resistor. Okay, beautiful. So here's our voltmeter. And you put the ammeter in series and you put the voltmeter in parallel, just like that. And when it says across the resistor, it means from one point and then on the other side of the resistor there. All right, so it has to be across it on either side. When the circuit is operating, the ammeter reads 0.5 amps. So I is equal to 0.5 amps. And that's super useful because it's a series circuit. So we know the current everywhere is 0.5. Even through the lamp, it's 0.5 amps. And through the resistor, we also know the current is 0.5 amps. Nice. It says draw a diagram of the circuit using the circuit symbols. Did that. Calculate the equivalent resistance of the circuit. So I would do for B, I would do R is equal to V over I. R is equal to the voltage, 12 volts. Total voltage divided by the current, 0.5 amps. So R is equal to 12 over a half, keep change flip, that's 24 ohms. That's the equivalent resistance. Then it says calculate the resistance of the resistor. You want to know what? Should we do the VERP table? It's kind of fun to do the VERP table. I want to have fun while I do this. I'm going to make a VERP table here. Okay, so I talked about how to do this in the previous videos. The voltage, the current, the resistance, the power in columns. And then in your rows, you have the different elements. So we have a lamp, a resistor. Typically, I do like 1 and 2. But I called it lamp and resistor here because it's fun. And then a row for the total. And my first step, I always try to remember to write series over here, so I remember the relationships for series is what we're using. And then you plug it in. So the total voltage is 12 volts. We don't know the voltage drop across each element yet, but we do know the current is 0.5 amps. Where am I going to put that? I put that everywhere because it's a series circuit. So that's super useful to know. And then the resistance of the lamp is 10 ohms. we don't know. Well, we just found the equivalent resistance. So see how we have two things in this row? Well, we know that we could use Ohm's law to find the other thing, and we did. We said it was 24 ohms. Okay, now it says calculate the resistance of the resistor. And this is why I kind of wanted to, if you use the VERP table and you're like, okay, let me see the resistor. I know the current. What else do I know? I don't have enough information in that row. Can I find it somewhere else? Oh, well, in this column, I know enough information to do the series circuit resistance, the equivalent resistance formula. And now you could say 24 ohms is equal to 10 plus R2. So R2 is going to be equal to 14 ohms. There you go. Now it says calculate the reading of the voltmeter connected across the resistor. So again, we're looking at the resistor here. And now we have two pieces of information in that row. And we could use Ohm's law to calculate the voltage. Let me set that up here. So this is the voltage drop. I guess we called it like 2, right? The second element. The current is the same everywhere, but the resistance is different. So V2 is equal to 0.5 amps times, we just said it was 14 ohms. So V2 is going to be equal to 7 volts. So this is 7 volts right there. Nice, nice. And part E says calculate the power dissipated by the lamp. The lamp is this row here. And we do have enough information to calculate the power. We have I and R. We don't have V, so we don't want a power equation with V. And we're going to look in our reference table for a power equation with I and R. So here's our list of power formulas. We want I and R. We definitely don't want V. So this one's no good. This one's looking good, and we can't use that one. So we're going to use I squared R to calculate the power. Then you substitute in. So 0.5 squared is 0.25. So 1/4 of 10 is 2.5 watts. 2.5 watts. All right. So moving on to this next one here, we could write 2.5 watts. Nice. 25. A 15 ohm resistor and a 20 ohm resistor are connected in parallel with a 9-volt battery. So let's draw that. It says a single ammeter is connected to measure the total current of the circuit. Okay, so we have our 9-volt battery. I always start with the battery. All right, and we want to know the total current. So I'm going to make sure that the ammeter's in the branch with the battery. And then we're going to split off into a 15 ohm resistor. There's our 15 ohm resistor and a 20 ohm resistor. Okay. Did that B, calculate the reading of the ammeter measuring the total current of the circuit. Looks like we're going to have to find the equivalent resistance first. Should we do a VERP table just for fun? I think I'll set it up. Why not? So this is for a parallel circuit, so the rules are going to be different from the previous one, and we have one element, two elements, and a total. Let's plug in what we know. The total voltage is 9 volts. Well, this is a parallel circuit, so we actually know the voltage everywhere now, don't we? That's sweet. The total current, we don't know any of the currents, but we know that this is 15 ohms, and this one's 20 ohms. Okay. Now, it says calculate the reading of the ammeter, so we're looking for this. We don't have enough information in the row, so let's see what we could fill in here. First, we have to use this column to fill in this information. Then we'll have enough info to use this row, to use Ohm's law. All right, so we're looking for the equivalent resistance in a parallel circuit. I'm going to give myself plenty of space. So here's the equation for parallel circuit, equivalent resistance. Then you substitute in for R1 and R2. Now at this point you could either deal with the fractions. Common denominator is a 60, so you would get 4 over 60 plus 3 over 60, or 7 over 60. Then you take the inverse, 60 over 7, and that'll give you REQ. Or you could plug it in your calculator and get this weird decimal, 0.116 repeating. And then to solve, you have to take the inverse of that. So REQ is equal to, and then in your calculator, you do 1 divided by, and then most people have, if you go second answer, that'll plug in that whole fraction for you. The answer is typically like the second function. You click on the negative button to do that. So 1 divided by second answer. Try to find that. It's a helpful thing. And you should get 8.57. A weird number, ohms. Really, if you wanted to be nice and with your future calculations, you could leave it as 60/7 ohms. All right. So that way, because this is a rounded number, 8.57. All right. So moving on. Now we know the equivalent resistance is 8.6 ohms, 8.57, 8.6, very rounded. We're looking for the current though still. So now we could use this row. We have two things. We have V and R. We could do I is equal to V over R. We could do I is equal to 9 divided by this rounded answer. So in your calculator, you could do 9 divided by second answer now, and you don't have to worry about the rounding, because if you do second answer, it doesn't round that number for you. And if you do it that way, it gives you exactly 1.05 amps. So that's our answer. We'll do like 1.1, I guess, amps. All right, 1.05. Let's keep it 1.05 because that landed up kind of nice. 1.05 amps. Now it says calculate the current through the 15 ohm resistor and the 20 ohm resistor. That's going to be less work because we already know the resistances of those. So it's not going to be 2 steps at least. So for the 15 ohm resistor, you take a look at your row, and thank goodness we have 2 pieces of information there. So we could just do I1 is equal to V over R1. The V is the same everywhere. So we have I1 is equal to, we have 9 volts divided by 15 ohms. So that's going to give you 0.6 amps. And we could do the same thing for I2 is equal to V over R2 is equal to 9 volts divided by 20 ohms. So you do that calculation and you get 0.45 amps. And take a look at that. Since we did the careful, like we try not to round our answer, and we got a total current of 1.05, and as you know, in parallel, the current in each branch, when you add them together gives you the total current. So 0.6 plus 0.45, that gives you 1.05, and everybody is happy. 0.6 amps, 0.45 amps. And I think, if I'm not mistaken, I think that's fine. Yes, that is. That's the end. That's it, people. All right, so that's electricity. Have a great day.